So now let's look at how to draw Lewis dot structures. So Lewis structures basically show you how atoms are bonded together, how atoms are connected together within a given compound. And there's actually a lot of different ways to draw Lewis dot structures, but I'm just going to show you one here that's basically based off of the book. So the first step here is to basically count the total number of valence electrons for the entire molecule. So for example, if we have ammonia, which has the chemical formula NH3, the total number of valence electrons for this molecule is 8, right? 5 coming from the nitrogen and 1 from each hydrogen. So a total of 8 valence electrons. And then the next step that you want to do here is to determine the total number of electron pairs. So you just divide the total number of valence electrons by 2 and you get 4. So 8 divided by 2 equals 4. So that means we have a total of 4 electron pairs. And then the third step here is to determine the central atom if there's more than 2 atoms. Typically, if you have carbon is almost always the central atom within that given molecule. Nitrogen in this case is going to be the central atom. Hydrogen, you might want to take note, will never be a central atom. Okay, so hydrogen is never a central atom. Carbon is almost always the central atom. Nitrogen, oxygen, boron, sulfur, phosphorus, chlorine, bromine, and iodine can also be a central atom. In ammonia, NH3, nitrogen is going to be our central atom. And then after you figure out which one the central atom is, step 4, surround the central atom with 4 electron pairs in order to satisfy the octet rule. So in this case, we have nitrogen, and we're going to distribute 4 electron pairs around it in order to satisfy the octet rule. And then step number 5, surround the central atom with the remaining atoms. So basically these remaining atoms will be the terminal atoms, the atoms outside the structure, the Lewis dot structure. So we have nitrogen, and we're going to place the 3 hydrogens surrounding the nitrogen atom. If there's any electrons left, distribute them equally among the rest of the atoms surrounding the central atom. Well, we had a total of 8 valence electrons in the beginning, and we distributed all 8 electrons to surround the nitrogen atom, the central atom. So now we have 0 electrons left to distribute. And then number 7, form double bonds or triple bonds whenever necessary to make sure that the octet rule is satisfied for each and every single atom, except for hydrogen, because hydrogen is considered stable with only 2 electrons, a single bond essentially. So hydrogen will never have a double bond or a triple bond. It will always be a single bond. So in this case, we've satisfied every single atom here. We have nitrogen, which has a total of 8 valence electrons surrounding it, and the hydrogens also have a complete outer shell, which contains 2 electrons. So again, this nitrogen right here has 4 electron pairs or 8 valence electrons, so that satisfies the octet rule. Hydrogen, each hydrogen atom has 2 electrons, which becomes isoelectronic with the noble gas helium. And so this right here is the Lewis dot structure for NH3, ammonia. So now let's take a look at a few examples here. We have CF4, NBr3, and CO2. So we have carbon tetrafluoride, nitrogen tribromide, and carbon dioxide. So the first step here is to basically count the total number of valence electrons for the entire molecule, for each molecule. Okay, so we're going to look at number of valence electrons total. We're going to divide that number of valence electrons by 2 to get the number of electron pairs. And then we're going to determine the central atom, and we're going to surround the central atom with electron pairs, and so on and so forth. So the first step is counting the total number of valence electrons. So carbon has 4 valence electrons, and each of the fluorine atom has a total of 7. So 4 times 7 is 28, plus 4, 32 electrons. What about for NBr3? So we have 5 for nitrogen and 7 for each bromine atom. So that's 3 times 7 is 21, plus 5, 26. And for carbon dioxide, 5 for carbon, 6 for each oxygen atom. So that's 2 times 6 is 12, plus 4 equals 16. Alright, so let's first focus on carbon tetrafluoride here. So we have 32 valence electrons. We're going to divide this by 2 and we get 16 electron pairs. And then now we're going to decide which one our central atom is. In this case, it will be carbon, because carbon is always a central atom. And we're going to surround it with 4 electron pairs, a total of 8 valence electrons. Alright, so we've distributed 4 electron pairs, 1, 2, 3, and 4. So we have a total of 16, subtract 4, and we have 12 remaining. 12 remaining electron pairs to distribute. So the next step here is to surround the central atom with the rest of the atoms. So we have 4 fluorine atoms, which will surround the central atom here. Okay, so it looks like this. And then we're going to distribute the remaining electrons equally among the 4 fluorine atoms. So we have 12 electron pairs remaining, and so divide that by 4 atoms. We're going to distribute 3 electron pairs for each fluorine atom. So 3 for this fluorine, 3 for this fluorine, and so on. Alright, and then we're going to double check whether each atom here needs a double bond or a triple bond. And as you can see, each atom already has a complete octet, meaning a total of 8 valence electrons surrounding the atom. So you can see for carbon you have 2, 4, 6, 8. So carbon is stable. This fluorine right here also has 2, 4, 6, 8 valence electrons, and so it's also stable. It's satisfying the octet rule. So shown here is basically the Lewis dot structure for the carbon tetrafluoride. What about for nitrogen tribromide? So again, bromine has 7 valence electrons times 3, 21, plus 5, 26. So we have 26 valence electrons total. Divide that by 2 and we get 13 electron pairs to distribute. And the central atom here will be nitrogen. Okay, so nitrogen is the central atom, and then we're going to surround the central atom with 4 electron pairs. So 13 minus 4, 9 remaining. So we have 9 electron pairs remaining to distribute. And so we're going to surround the central atom, nitrogen, with the 3 bromine atoms, the terminal atoms. Alright, so you can see, and we have 9 more electron pairs to distribute, and we're going to distribute them evenly among the 3 terminal atoms in order for them to satisfy the octet rule. And so 9 pairs divided by 3 atoms, 3 electron pairs. So each bromine will receive 3 electron pairs. Alright, and you can double check if each atom has 8 valence electrons, then they're stable. Okay, they've satisfied the octet rule. And so we don't need to form any double bonds or triple bonds because of this. Alright, and the last one here is carbon dioxide. Carbon dioxide has a total of, let's see, we have 2 times 6, 12, plus 4, 16 valence electrons. So we're going to divide that by 2. 16 divided by 2 is 8 electron pairs. And then carbon is our central atom, and we're going to distribute a total of 4 electron pairs, and we have 4 remaining, 4 electron pairs to distribute. And then we're going to surround the central atom with the remaining atoms, the terminal atoms, in this case oxygen, and then distribute the remaining 4 electron pairs evenly, right, equally among the terminal atoms. So we have 4 electron pairs, divide that by 2 atoms, we have 2 electron pairs to distribute to each oxygen atom. Alright, so as you can see here, carbon is happy with 4 electron pairs, a total of 8 valence electrons, but for oxygen, each of the oxygen atoms only has 6 valence electrons, and so they're lacking 1 electron pair, or 2 electrons. So let's take a look. How can we form bonds, right? Double bonds or maybe even triple bonds in order to satisfy the octet rule. So let's take a look. So carbon must form a double bond with each oxygen atom in order to satisfy the octet rule. So you have this pair of electrons right here and this pair of electrons right here that are non-bonding at the moment, right? They're not involved in bonding. The only pairs of electrons that are bonding are these electrons right here, right, in between the carbon and the oxygen. So this is a bonding pair. This is another bonding pair. These two up top and the bottom are both non-bonding pairs. And so we have to get them involved in the bonding in order to satisfy the octet rule for both the oxygen atoms. All right. And so carbon will share its non-bonding lone pairs of electrons with the 2 oxygen atoms. And so what's going to happen is we're going to move them around a little bit, and we're going to put one of the pairs on the right-hand side and the other pair on the left-hand side, as shown here. So this right here is the Lewis dot structure for carbon dioxide. So it contains a double bond. All right, so we can show you the simplified Lewis structure for these 3 molecules here. So we have the pair in between carbon and fluorine and replaced it with a single bond. All right, so you have carbon, the carbon, central carbon, that's now single bonded with each of the fluorine atoms. And in NBr3, we have the nitrogen that's single bonded to each of the bromine atoms, and so on. So the next 2 concepts that I want to cover here are resonance structures and formal charge. So by definition, resonance structures are Lewis structures of the same molecule that have the same atoms in the same locations, but different electron arrangements. So what that means is that you have one single molecule with multiple possible Lewis structures. And so the difference between the structures is in the arrangement of their electrons. So that means that one structure might contain double bonds and triple bonds, and then the other structures don't have any double bonds and triple bonds and only single bonds. Okay, so the atoms are connected to the same atoms. The only difference is the arrangement of the electrons. So let's take a look at an example here. Let's say we have this carbonate ion, which is a polyatomic ion with a -2 charge. Draw its Lewis structure and any resonance. So the first thing that you want to do is count the total number of valence electrons for this ion. So we have carbon, which has 4 valence electrons, and each oxygen atom has 6 valence electrons. So 6 times 3 is 18, plus 4, 22. And then there's this -2 charge here, so we're going to add 2 electrons to the 22, so we have a total of 24 valence electrons. So again, 3 times 6 is 18, plus 4, 22, plus 2, a total of 24 valence electrons. So we're going to divide 24 electrons by 2, and we get 12 electron pairs. And then we're going to surround the central atom, which is carbon, with 4 electron pairs. And then we're going to surround the central atom, carbon, with the terminal atoms, the oxygen atoms. All right, and so how many electron pairs do we have remaining? So we have a total of 12, and then we distributed 4 electron pairs, so that's 12 minus 4. We have 8 pairs remaining. So how are we going to distribute 8 pairs of electrons equally among 3 oxygen atoms? Well, we can't, right? We have 8 divided by 3 is a fraction, so we can't really do that. So one of the oxygens will only have 6 electrons, or a total of 3 electron pairs. And so we can distribute 3 electron pairs here for this oxygen, and then 3 for this other oxygen, and then 2 for the third oxygen, for a total of 8 electron pairs. All right, so as you can see, this oxygen right here has one pair lacking, right? So it lacks 2 electrons, or 1 pair of electrons. So what that means is that this carbon right here has to share its lone pair, which is a non-bonded electron right here, with this oxygen. All right, so this right here is one possible structure of the carbonate ion. As you can see, we have each oxygen atom has full octet. This oxygen right here has 2, 4, 6, 8 valence electrons. This carbon also has a total of 8 valence electrons, 2, 4, 6, and 8. All right, so every single atom here satisfies the octet rule. And this is one possible Lewis structure for the carbonate ion. What about any resonance? Does this have any possible resonance structure? Well, according to the definition of a resonance structure, you have the same molecule with multiple different Lewis structures. And you have the atoms that are bonded to the same atoms, and the only difference is the placement of the electrons. So in this case, we can move the double bond over here to this oxygen. So instead of a double bond with this specific oxygen, we can move it and place it on this middle oxygen here. So that is another possible structure of the carbonate ion. And then a third possible structure is a double bond with this oxygen on the left. So all these structures shown here are the resonance structures of the carbonate ion. And the next concept here is regarding formal charge. And by definition, formal charge is the charge an atom would have if all bonding electrons were shared equally between the bonded atoms and electronegativity effects are ignored. So formal charge is basically the charge an atom would have if we ignored the electronegativity effects. So how do we calculate the formal charge of an atom within a Lewis dot structure, within a given molecule? So we can use this formula here for formal charge. So formal charge is equivalent to the number of valence electrons of an element minus the number of non-bonding electrons around it minus the number of bonding electron pairs. So make sure that you remember this formula for formal charge. You're going to use it and you're going to need it for the next test. Alright, so let's take a look at an example here. Determine the formal charge of each oxygen in the following Lewis structures. So we have 3 different structures here, and these are 3 different molecules. Okay, so we have molecule 1 on the left, molecule 2, molecule 3. So these are all 3 different molecules, and they're not resonance structures. All right, so for the first one, how do we calculate the formal charge for the oxygen atoms? Well, we can use that formula for formal charge. So here's the formula again, shown at the bottom. So the formal charge is the number of valence electrons of the element minus the number of non-bonding electrons minus the number of bonding electron pairs. And so here, we're trying to determine the formal charge on the oxygen atoms. So looking at this oxygen right here, we know that oxygen has 6 valence electrons, and then we're going to subtract the number of non-bonding electrons. So this oxygen has a total of 4 non-bonding. So 6 minus 4 is 2. And then we're going to subtract the number of bonding electron pairs. And this oxygen has 2 bonding electron pairs right here. Remember that a single bond contains 1 electron pair, 1 bonding electron pair. So in this case we have 2. So again, 6 minus 4 is 2, minus 2 is 0. So this oxygen right here has 0 formal charge. This oxygen is basically similar to this oxygen on the left, and so this oxygen on the left will also have a formal charge of 0. In other words, neutral. All right, and what about this second molecule here, second Lewis structure in the middle? So we have carbon that's double bonded to an oxygen, and so on and so forth. So this oxygen right here is basically similar to these 2 other oxygens in the first molecule. And so this oxygen would have a 0 formal charge as well. And you can always double check that. So oxygen has 6 valence electrons minus 4 non-bonding electrons minus 2 bonding electron pairs. So that's 0. This oxygen right here is similar to this oxygen on the left. And so again, they would have the same formal charge. So 6 valence electrons minus 6 non-bonding electrons minus 1 electron pair. So that would be a negative 1. So this oxygen right here has a negative 1 formal charge, and this oxygen over here would also have a negative 1 formal charge. So again, 6 minus 6 non-bonding electrons minus 1 bonding electron pair. All right, and the last one over here is carbon monoxide. So what would be the charge on this oxygen atom over here? So again, the formal charge equation or formula is the number of valence electrons, which is 6, minus the number of non-bonding electrons. 6 minus 2 is 5, minus 3. So that's a positive 1. So this oxygen has a positive 1 formal charge. So let's do a little practice here and also try to determine the formal charge on this carbon atom in carbon monoxide. So carbon in the periodic table is in group 4, so it has 4 valence electrons, and subtract 2 non-bonding. 4 minus 2 is 2, minus 3, and that would be negative 1. So this oxygen right here has a positive 1 charge, positive 1 formal charge, and this carbon right here would have a negative 1 formal charge. So here's a few important points that you should remember regarding formal charge. The first one here says the sum of all formal charges in a neutral molecule must sum up to 0. Okay, so when you add up all the formal charges for a neutral molecule, it should equal 0. The second one says the sum of all formal charges in an ion must equal the charge of that ion. So like for example, we looked at carbonate ion earlier with a negative 2 charge. When you take the sum of all the formal charges, it should equal negative 2. The third one here is small or 0 formal charges on individual atoms are better and more stable than large ones. And the last one here, when formal charge can't be avoided, negative formal charge should be on the most electronegative atom. And that's basically true for regarding stability. So you don't want to put a positive charge typically on an electronegative atom unless you just have to. But usually a negative formal charge is given to the most electronegative atom. All right, so let's take a look at a few examples here. Based on formal charges, which Lewis structure do you think is more stable? So we have the molecule HCN. Okay, so hydrogen cyanide, HCN. Which one do you think is more stable? Structure A or structure B? Well, let's take a look and use the rules when it comes to formal charges. So to determine the formal charge, we have to look at the number of valence electrons for each atom, and then the number of non-bonding electrons, followed by the number of bonding electron pairs, and then we're going to subtract them, and we'll get the formal charge. So hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5 valence electrons. All right, and then the number of non-bonding electrons for hydrogen is 0, for carbon is 0, for nitrogen there's 2 non-bonding electrons for structure A. For structure B, 0 for hydrogen, 0 for nitrogen, 2 electrons for carbon. And then in terms of bonding electron pairs, hydrogen has 1, carbon has 4, nitrogen has 3. And for structure B, hydrogen has 1 bonding electron pair, nitrogen has a total of 4 bonding electron pairs, and carbon has 3 bonding electron pairs. Alright, so now all we have to do is subtract these numbers and we'll get the formal charge. So 1 minus 0 minus 1 equals 0. 4 minus 4 is 0. 5 minus 2 minus 3, 0. And for structure B, we have 0 for hydrogen, positive 1 for nitrogen, and negative 1 for carbon. So as you can see, based on the rules regarding formal charge, you want to minimize the formal charge on individual atoms. So if you minimize them, then you have more stable electron structure or Lewis dot structure. So in that case, this structure right here, structure A, is more stable than structure B based on the formal charges. So every time you draw the Lewis dot structure for a molecule, you always have to take into account the octet rule, right? That every atom in the Lewis structure has to have a total of 8 valence electrons. But there's actually an exception to this rule, and there's a few of them. So let's take a look. The first one here is incomplete octet. So there are some elements in the periodic table that don't have to have a complete octet, 8 valence electrons. For example, helium was the first one that we looked at, and hydrogen, right? Those elements don't have to have 8 valence electrons in order to be stable. Beryllium is the same way, and boron. So these elements, they can bond and form 3 bonds with only 6 valence electrons and be considered stable. So we have beryllium, boron, and hydrogen, as well as helium. So we have 4 elements that don't have to follow the octet rule. So an example here is boron. Boron can form 3 single bonds with fluorine, and it can also form 3 single bonds with hydrogen. Okay, so as you can see here, this boron right here only has a total of 6 valence electrons and still would be considered stable. Same thing goes for BH3. So this boron right here has 6 valence electrons and still stable. These hydrogen atoms right here only contain 2 valence electrons, and they are also considered stable because of the fact that they are isoelectronic with helium. These elements, boron for example, can complete their octet via chemical reactions. So for example, BF3 can react with ammonia, NH3, in order to complete its octet. So this is basically organic chemistry type of reactions where you have an electron deficient boron and electron rich nitrogen. So the electron rich nitrogen, which is basically the electron donor, will donate its lone pair of electrons with the boron, and so they form a bond. They form a bond between them. So you have boron that's bonded to nitrogen, and so nitrogen in this case would gain a positive charge, formal charge, and the boron would gain a -1 charge. Another exception to this rule is expanded octet. So that means that there are certain elements in the periodic table that can accommodate more than 8 valence electrons. Okay, other elements such as those in the third row of the periodic table and beyond can have or hold more than 8 valence electrons. And some of them can even occupy up to 12 electrons. And the reason behind this is that these elements on the third row and beyond can access their d orbitals. So they can use their d orbitals to form those bonds. So let's take a look. So we have arsenic, AsF5, SF6, sulfur hexafluoride, and sulfate ion. Okay, so let's take a look at their Lewis dot structures. So as you can see here, this arsenic has a total of 5 single bonds, and each single bond contains 2 electrons. So that's a total of 10 electrons surrounding this element. What about sulfur hexafluoride? Sulfur has a total of 6 single bonds, so that's a total of 12 electrons. And finally, we have sulfate ion here with a -2 charge. And this is the Lewis dot structure for sulfate ion, and it has a few resonance structures. As you can see here, this sulfur also has a total of 12 electrons, valence electrons. 2, 4, 6, 8, 10, and 12. One other concept that I want to talk about here is bond energy and bond length. So bond energy is basically the energy required to break that bond. And this is usually a positive value, because in order to break a bond, you have to input energy into the system in order to break that bond. Triple bond requires more energy to break than a double bond or a single bond. So that means that a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. So here's a few examples. So we have carbon-to-carbon bond. So this triple bond right here is stronger, right? It has a higher bond energy than a carbon-to-carbon double bond. And a double bond is greater in energy than a single bond. You can also look at it in terms of 2 different elements, like carbon-to-nitrogen bond. So you can have a triple bond between carbon and nitrogen, and this is greater in energy than a carbon to nitrogen double bond or a carbon to nitrogen single bond. And bond length represents the average length of a bond between 2 atoms in a number of compounds. Single bonds are typically longer than double bonds or triple bonds, and so single bond is the longest, followed by the double bond and then triple bond. And the reason why is because of the sharing of electrons in covalent molecules. So in order to share more electrons, you have to get closer to the nucleus. You have to get closer to the atom itself in order to access those electrons. So here's a few examples. Again, you have carbon-to-carbon single bond or carbon-to-nitrogen single bond, carbon-to-oxygen single bond. And these single bonds are much longer compared to the double bonds, and the double bonds are longer than the triple bonds. So it's basically the reverse, right? So the energy is when the energy of the bond is high, the length of the bond is short. Okay? So that's the relationship between bond energy and bond length. And the last concept that I want to cover here is regarding metallic bonding. And this is basically the bonding in metals. When metal atoms bond to form a solid, each metal atom donates 1 or more electrons to an electron C. Right? So this is basically an electron C model. So you have a bunch of atoms, metal atoms, that donate electrons to the pool of electrons. So here's an example. So you have sodium metal, and this sodium metal has an array of sodium ions submerged in a sea of negatively charged electrons. So you have sodium ions that are submerged in a sea of electrons, and these electrons are delocalized over the entire piece of metal. Okay, meaning that the electrons are not localized on one spot, but rather it's equally shared by all the atoms within that given piece of metal.